Hello, EOS 110. This is a tutorial about calculating different properties of a wave. We learned in class that a number of properties of the wave, such as its speed, wavelength, and period, are related to each other. Sometimes those relationships hold in all circumstances, and we saw at other times they only hold for particular situations. Let's start out with the equation that always applies. We saw that the phase speed is equal to the wavelength divided by its period. Remember, the wavelength is the distance between two crests or between two troughs of a wave, and the period is the travel time. So think about one crest passing and you begin timing it, and when the second crest passes, that's the end, and the length of time there is the period. Now this has units of distance or length at the top divided by time at the bottom. So this is one equation that we'd expect you to remember. And the way to remember it is think about driving your car and what's your speed, right? We think about our speed in terms of, say, kilometers per hour, which is the distance you travel, divided by the time it takes to travel that distance. So same thing here, distance divided by time. And this is a relationship that always applies no matter what the water depth. Okay, so let's do some examples of this. Let's say we have a 15-second period wave. And that it has a 350 meter wavelength. Okay, then its phase speed, and we call it the phase speed because it's the speed of an individual wave. That's different from the group speed that we learned about also in class, which is the speed that a packet of waves travels at. Okay, so we want phase speed equal to wavelength, which we said was going to be 350 meters for this example, divided by a period, which we made 15 seconds. We have 350 divided by 15, 23.3. And the units here are meters per second. Meters per second. Okay, well really if we know any two of speed, wavelength, and period, we can calculate the third one from this equation. So let's do a couple of other examples. Let's say we knew the period, 15-second period again, and we knew its speed, 23.3 meters per second, and we wanted to calculate the wavelength. If we come up here back to this equation, we can see that if we bring period out from being here in the denominator and multiply it over here instead, we'll be able to solve for wavelength. So we would have phase speed times period equal to the wavelength. And our phase speed is 23.3 meters per second. Period is 15 seconds. So if we multiply those two together, we get 350 meters approximately. Okay, let's do one more. Suppose we knew the phase speed. Let me just mark this here so we remember. Say we have our phase speed of 23.3 meters per second, and we have our wavelength equals 350 meters still. Can we calculate the period? Let's come back up here to this equation. We can see we could calculate period if we divide both sides by the phase speed. We get period equals wavelength divided by phase speed. Or in this case, we have 350 meters for our wavelength, 23.3 meters per second for our phase speed. 350 divided by 23.3. Indeed, we get 15 seconds. So we see here that if we know any two of these three properties, phase, speed, wavelength, or period, we can solve for the other one. And again, that doesn't depend on what water depth that we're in. We also learned in class that there's a relationship between wavelength and period. And that there is a relationship, in fact, that applies over any water depth. It's just that it's a more complicated equation than we'd like to use given the prerequisites of this class. However, when certain situations apply relating the wavelength to the water depth, we find that that equation simplifies and we do get an equation that's appropriate. So the first situation we want to consider is that of a deep water wave. And this is a situation when the water depth is greater than, so deeper than, 1/2 of the wavelength. It's really important to think about the relationship between water depth and wavelength when deciding if something is a deep water wave or, as we'll talk about in a minute, a shallow water wave. And the reason is that there are, even in the open ocean where the water depth is 4,000 meters deep, waves that are not deep water waves. And two examples of that we learned about in class were tsunami and the tide wave. And both of those have wavelengths that are so long that they don't, that half the wavelength is still quite a lot more than the water depth. So those would not be deep water waves. But the average wind wave that is traveling out in the open ocean is a deep water wave. Okay, so in this situation where the water depth is greater than half of the wavelength, then we find that the wavelength is related to the period this way. Wavelength is equal to gravity divided by 2 pi times the period squared. All right, so let's look at that for our 15-second wave. We have wavelength equal to gravity, that's 9.8 meters per second squared, divided by 2 times 3.14 is pi, times the period, which is 15 seconds squared. Okay, so we can calculate that. 15 times 15 gives me 15 squared times 9.8 divided by 2 divided by 3.14. And I get 351 meters. Okay, the other situation we talked about was when the water depth is shallower than 1/20th the wavelength. We call this a shallow water wave. When the water depth is less than, i.e. shallower than, 1/20th of the wavelength. So in the open ocean, that requires quite a long wavelength, but again, tsunamis and the tide wave both achieve it, and these work as shallow water waves in almost any depth in the ocean. But for a wind wave, those have to get very close to shore, where the water depth gets small, in order for this relationship to apply. And the relationship we're talking about is one where the speed of the wave is equal to the square root of gravity times the water depth. So here we can see that all waves travel the same speed once they become shallow water waves, because they only depend on the water depth. The wavelength or the period no longer matters in that case. So let's do a calculation for a situation with a depth of, say, 2 meters. And here we can see that the speed would be the square root of g 9.8 meters per second squared times 2 meters. Okay, so I'll take 9.8 times 2 equals, I'll take the square root of that, 4.4. meters per second. So we can see that the wave here in 2 meters, say it was our 15-second wave still, it was traveling 23.3 meters when it was out in the open ocean, but now that it's come close to shore, it's really slowed down and it's traveling at only 4.4 meters per second. And as it further approaches the shore, it will slow down even more. Okay, I hope this little video has helped understand some of the calculations that we do in class relating different wave properties to each other.